Okay, so in today's lecture, we're going to continue with sequential logic. And then I think the most important part in sequential logic is introduced in the previous lecture, so sequential logic 1. But today we're going to solidify it and introduce you with some basic concept of the sequential, some building blocks for sequential logic. And then eventually we can use these sequential logic elements to build CPU cores or other memory storage unit. Okay, so as a review, sequential logic, here we're considering sequential logic is a digital circuit. Its output depends on the prior state, and the prior state is stored in the memory, which is typically considered we typically use registers as the memory there. Now we have feedback signal, and the whole circuit is controlled by clock. So like last time we talked a lot about how latches work and how register works, but basically I think you can forget about detail about how latches work and register work and only care about registers can guarantee that the data can pass at the rising edge of the clock signal or the down edge of the signal. It depends on the design, but it will only respond to one edge of the signal and can pass the signal through, right? Then for the rest of the clock cycle, it will latch the signal there. Then when we're talking about sequential logic is it's on the contrary to combinational logic circuit. In combinational logic circuit, we don't have memory, and for any input, then we have a kind of predetermined output. Right. Then we also consider this combinational logic can generate result in one shot, like it takes no time. But for sequential logic, we consider in one cycle it will generate some intermediate result until eventually it will get some final result. Also, sometimes this intermediate result is also important for sequential logic. And combinational logic is still very useful because it describes the behavior of this, the behavior of the whole circuit, right? If you consider a memory, it can only record the state of the circuit, but the combinational logic should decide what's the behavior of this logic of the circuit. Then the most important part is the register. As we said, it only responds to the rising edge of the clock signal, and when to rise edges, then the output signal can change, and for the rest of the whole cycle, for the rest of the whole clock cycle, it will keep this value unchanged. Okay, so a register basically captures the input data at the moment of the clock edge and holds the value constant until output value constant until the next clock edge. That's all you need to remember about what is a register. Forget about how it's implemented with SR latches and even two SR latches and NOT gate. But here, as we're going towards higher level of the design stack, we don't really need to remember the gate level design. Just consider register as the most fundamental element of a digital circuit design. Okay, so okay, so we also talk about finite state machine and how to use a finite state machine, FSM, to design a digital circuit. Now, finite state machine is basically a machine. It's not really a hardware. It's a concept that if we follow these steps, then we can achieve some goals. It's a concept that we model some hardware, some circuit mechanism so that it can work in this way. So we define a few states, right? In this case, this is the figure from the last slide, from the previous set of slides. We define these traffic lights with a few states, right? S0, S1, S2, and S3. Then 4 states, and each state decides what's the output of the whole circuit. Then I try to list a general step of steps to define what we need to do to use finite state machine to design a sequential logic circuit. The first step, let's try to list all the possible output. Now list all the states. These two can be directly related. In this case, for example, in this case, our output is basically S0, S1, S2, S3 maps to either red or green or red, yellow states, right? For some cases, as we'll see in a later example today, they may not be directly related. Then we can draw the state transition diagram. We can see which state transit to which other state. Then we can encode the state and the output. Say in this case we have 4 states. When I have 4 states, we can use 2-bit. If I have 5 states, we need to use 3-bit. Then we need to encode the state, and the encoding order typically doesn't really matter. You can change the order as long as it's one-to-one mapping. That's good. Then list the state transition table, right? We list the state transition with 1 arrow per entry in the table. Then we write down the encoding so that it turns into a truth table. Now for the current state, and the input is the input to the combinational logic. Then the next state and output are the next state are the output of the combinational logic. So using that truth table, now I think for the combinational logic lecture, the most important lesson is whenever I give you a truth table, you can draw a circuit, right? Like just gonna take some time. You can draw a circuit. In this case, we have a truth table. Then you can write down the Boolean expression and simplify it, and eventually draw the circuit, right? So then that's the whole step of designing a sequential logic circuit. So let's give a few actual example or slightly more advanced example to just to help you understand the whole process about how to use finite state machine to design a digital circuit. Let's consider this type of door lock. There are 12 keys. We probably will only care about let's only care about 10 keys. Say if I type 4 numbers, when I type 4 numbers, then if it's correct, then the deadbolt lock unlocks, right? If I type the wrong number, I still need to type 4 of them, then click on the check mark, then it will try to unlock it. But if it's a wrong number, it will just generate, say, a boot noise. Then it will tell me it cannot unlock because the passcode is wrong. And there can be a lot of advanced design to this. For example, people can design this thing like if someone is following you but you still not want to reveal their true password, you can type 8 numbers. So as long as 4 numbers as a sequence in these 8 numbers are correct, you can unlock the key. So after we talk about this example, I think you should be able to design some more advanced features by adding more state in this in the state diagram. But let's try to use the very simple example to try to demonstrate again how finite state machine is used. Okay, so what's the finite state machine? Then the finite state machine, try to draw this one in this way. This is my finite state machine. If you draw the finite state machine, you can draw a totally different one, and you may even have different number of states and to map different output or different actions. But let's try to go through this one and see if you can understand it or not. Okay, and still, I don't think there's a certain way to implement it. To draw this diagram, you can draw a totally different one, but still perfectly correct. So in finite state machine, I think actually for most of the time, for 99% of the time, we start with an idle state. Then in this idle state, that is the initial state, right? So also whenever we need to reset, we come back to this idle state. So if we click the cross mark, then it always go back to the idle state so that we can type in the password again. So then we can press the first digit, but when we press the first digit, it can be either right or wrong, right? It can be correct or wrong. If it's correct, we go to C1. If it's an error, we go to E1. Why there's a state? Because we cannot really directly tell if the user this is correct or not, right? If user press the first one as a wrong number, then it's much easier for a malicious user to guess the correct passcode. So we go to this E1, but this E1 from the output, this is a totally hidden state, right? Because even the C1 and the E1 is actually not going to generate any output at this point, but it's only an internal state that will remember the current state so that we can progress to future states, right? So in this case, we have this E1 if user press the wrong number, and C1 if this user correct the right number. Then continue as we keep pressing the right number. I think there should be errors. There's actual errors. So starting from C1, if we correct the wrong password, we actually can go to E2. Then if we press the right number, it goes to C2. Correct number goes to C2, and wrong number goes to E3. Okay, but if you are at E1, if you are at E state, error state, you always need to go to E state, no matter what number you pressed, right? E2, E3. And if you press something from E3, you press the fourth number, then you always go back to idle state. But if you are in C3 and press the correct password, you go to unlock. Now it takes a little bit time to stay in the unlock state. Then in this state, we unlock the dashboard. Then typically there's another sensor to detect if the motor finishes rotating. It will stay in this unlock state to emit signals so that the motor is rotating until the dashboard is fully retracted. Then at that point, we go back to the idle state so that we can lock it later. This whole machine is only about unlocking process, and we're not talking about locking process. Okay, so if you are interested, definitely you can design something more fancy, but let's start with something that is manageable, that I can show things in one slide. Okay, this is the state machine of this logic. Then the next thing is we're going to use state encoding. So how many states are there? Then there are 8 states, right? So C1, C2, C3, E1, E2, E3, there's 6 states, and idle and unlock are 2 states. So there are 8 states. With 8 states, we can use 3 digits to encode the encode state. Then for this type of device, probably there's a very, very simple chip behind it that's controlling the state. Every bit counts. So we want to save the bit. And actually, if you ask me what type of controller is actually controlling this one, it's very, very unlikely it's a ASIC. It's a application specific chip. This type of company, for this type of device, is very unlikely that they build a chip for this type of device. It costs too much money. So what they are using is something called a microcontroller. Then the microcontroller typically can write some C code in it and can run some instruction, super simple instruction in it. And there are some pins. So the state machine is still useful, but is most likely implemented in this type of microcontroller in a software, not really directly in the hardware. But if you want to design something like this, or digital clock, something like this, ASICs are still useful. And those are toy examples for more complex computer chips. Okay, so we have this encoding. Then we start to work with the state transition. Then let's say this is not my final state transition table, but let's try to see it and see if you can understand it. If we're starting in idle case, or encoding is 0, 0, if our input is 1, so I'm assuming my passcode is 1, 2, 3, 4, okay? Just any passcode works, but let's just make it simple, 1, 2, 3, 4. If it's 1, we go to C1 state, right? If it's anything else that is not 1, we go to E1 state, arrow 1 state. Now starting in C1 state, if our input is 2, now our state is C2 because it's correct again. Now if it's not 2, we go to E2 state. Now if we start in E1, no matter what we typed, any number, not including the check mark and the cross sign, we go to E2 state. Similarly, if we're in E2, we go to E3. If we're in 3, we go to idle, right? Now, if we're in C2 and our input is 3, we go to C3 state. If we're otherwise, we go to E3 state. Then in C3, if the input is 4, we go to unlock state. Otherwise, we go to idle state because the last digit was wrong, right? Then in the UL, in the unlock state, no matter what's the input, we go to idle state. Okay, so I think this state diagram is basically a simple, it's a direct translate of this state diagram, except this state diagram should have this arrow from C1 to E2, C2 to E3. Okay, so any question with this design, any problem with this design? Yeah, you can try a lot of times. You can always try a lot of times. Then you may have some like delayed locking, but that's too advanced for this type of device.
After going to C3, like the correct order, okay, it's going to the idle one again, the state.
C2 can go to idle one.
C1, C2, C3, and then in idle.
Yep. So I think your point is any state can go to idle state.
Yeah.
If the cross sign is clicked, right? Yes, so in that case, we typically consider a reset signal. Like the cross sign is a reset signal. When that button is clicked, if we draw a state diagram, we just directly put an arrow out of nowhere, just pointing into the idle. So that it means no matter what state, even in the state that is not described in this case, so in some particular hardware, that is possible that, for example, if you have 10 states, but you use 4-bit to encode your state, then if you're something wrong, there's some bug with your hardware, then eventually you are going into a state that doesn't exist. Then you can always use a reset signal to go back to the initial state. So that's a reset signal. In that case, we typically draw arrow into the idle state whenever that button is pressed. But in this case, I think it's rather standalone input, right? So that's why I didn't include that part into this table. The problem is, what is triggering the state transition? The press is triggering, right? Even the unlock, like probably it's a sensor detecting this motor is fully retracted, this bolt is fully retracted, then we consider it's done with this unlock state and becoming the idle state. Does it work? Then it's not ideally work because we prefer to use clock signal to control the state transition, right? So what's wrong with using press to detect the state transition? It's typically if we press a button, then you feel that this button is clicked, there's from 0 to 1 transition. But in fact, there are like when it's contacting, when two pieces of metal contact each other, the voltage will actually flutter a lot. So how many times, I don't know if you'll try this, now without any detection mechanism, it will actually, like if press a button, like for every time if it's positive, then you add a counter by 1. Then you can easily add to tens of thousands by just one quick press, right? So no device is perfect. So in that case, if you press one button, you may easily go hundreds of cycles through this state diagram because your clock signal is much faster than the press, right? If you feel the press is a one shot, but it actually takes a small transition period, and compared to megahertz processor, well, this type of processor at most runs at the megahertz level, then it's already several thousand, tens of thousands cycles. So that's a problem. We prefer to use clock signal to control this. Now, how we can use clock signal? That means if user didn't press anything, we should go back to the original state. For example, if we're at state C1, and for user didn't press any button, that means all the key, say each wire, let's consider one wire is one button, right? So all the wires are 0. If in that case, we should stay in the original state, unchanged for most of the signals. So, well, I forgot this slide. So I think if I draw this thing, you should be able to write this equation, right? Now we have been talking about this for many times. I only write S2 here, this one. S2, the most significant bit of the encoding. So if you look at, it's 1 here, 1 here, 1 here, 1 here, 1 here, 1 here. Then there are several ones there. Then we can write down the equation in this way. I think I try to simplify it a little bit, but it can be simplified a little bit more. Now this is the case. These are if we consider button press as state transition. But as we said, we don't want the button to trigger state transition. We want the clock to trigger state transition. About how to transit the state diagram is really depends on the input, right? So you can see there are many more state transition entries in this table. For example, if we're in the idle state, now our encoding is 0, 0, 0, and input is none. That means all the input wires are 0. In this case, our next state is still idle. And then the output encoding is still 0, 0, 0. Then the idle, now in this case, C1, right? For every state, the first entry is always if the input, no, I think there's a mistake. So for C1, now if the input is none, we should state in C1 state. And this encoding is also wrong. Okay. If we're in C1 state, right, no button is pressed, we should stay in C1 state and the encoding should stay in 001. Right? So those are more cases in this state transition diagram. Now in this state transition diagram, we draw, this is the case, in this case we draw all the possible cases and all the signals. Then, okay, we're okay with this design? Then, if you consider input signals, other than this 3-bit encoding, we actually have 10 digits, right? We have 10 digits, so there are 14 input wires to this combinational logic. Now remember, when we are dealing with kernel map, we're only dealing with 4 possible input, right? In this case, pretty much we cannot use a kernel map. The only thing we can do is to write down equations. I put a none there. That means if all of them are 0, then we consider this none to be true, right? So in this case, I'm trying to write down this equation here. Let's look at it together. And in this case, I think we're trying to write down the minterm, right? So this minterm, this next encoding N2, this one is 1, so we're trying to write down this term. Then C1 is basically this state is 0, 0, 1, which maps to S2 prime, S1 prime, S2, right? Now in this case, we consider I2 is not pressed. I2 is not pressed, and none is also negative. That means some other button is pressed. if you want to expand this non-signal, there are many terms. It's I1, I0, or I1, or I3, or I4, right? That's the non-signal. It's either one of other signals are being pressed. So we know I2 is not pressed, but some other button is pressed. In that case, we generate an output of 1. And similarly, we can write down every minterm here following the same idea. Then this is the equation of the whole state transition diagram. That's for the S2 bit. This is the S2 bit. Now for S1, you need to generate another equation, and for S0, for N1, you need to generate another equation, and for N2, you need to generate another equation. Then eventually you can draw a circuit to express the circuit to be designed. Okay, so this is a more concrete example to design a sequential logic with a state diagram. Okay, then my goal is for this type of problem, if we're limited to a few input or the logic is relatively simple, I want you to be able to eventually draw the circuit with a register sign and the gate sign, and then to express the whole logic. Okay, and also you should at this moment feel confident that this part, even if it's difficult, for example, if my register, well, we have a 1000 bit register, then we have 200 input. Okay, then you know, in theory, you can design this type of sequential logic circuit that can always transit from a state to another state, then eventually generate the correct output, right? No matter how many input you have, how many bit of the state you have, eventually you can draw this type of diagram. Then you can draw the circuit. It just will take years of time, but if you use a computer, the computer write a program can help you, then eventually you can design this, right? So how complex this type of combinational logic or this type of state diagram that we can eventually have? It's basically unlimited amount of state that you consider. GPU may have thousands of registers. In GPU, a register typically is 4-byte data. Okay, every register is actually 32 1-bit register. Okay, in that case, you should still, like, if we know the rule, then it can be expressed by some sort of state machine. Then eventually we can design some very complex circuit, right? So you should be confident about that. Let's say the building block, although I don't exactly know what's the building block of a CPU chip or a GPU chip, but I know in theory it can be designed. And if I can describe the rules, how the state transits, what's the calculation rule, then a computer program can help you eventually design a circuit, laying out all the gates necessary. Okay, that's the goal of this part of the lectures until this part. Eventually, you will, if you do computer architecture research, you probably don't need to remember all these things, but only the key principles of this part, and have the confidence saying, oh, this is something possible. Then eventually you can tell, if I give you something, some requirement, you can tell me, oh, this is likely to be possible, right? Okay, so that's a state diagram, and that's actually a little more review about state diagram. Let's try to go the other way around. If we have a circuit diagram, can we derive the finite state machine? Okay, this circuit diagram. Then this is circuit diagram. Eventually, I want you to draw if I have a simple state machine, right? This is circuit. Then, so whenever you see this type of sign, this is a register. And how many bits are there in this register? Since we're drawing output S1 and S0, and we have N1 and N0 as input, we know there are 2-bit output, 2-bit input. That means this register There are actually two 1-bit registers there, right? We draw it together so it represents one set of state, right? You will see eventually in pipeline CPU design, this is a division of the pipeline stages. But we have this register. Now in this register, S1 is directly outputting or directly connecting to the analog output. Then S1 and S0 are connecting back to some gates, to two AND gates and some inverters. Eventually it generates to N1 and N2. We have a reset. Reset is not that important here. Then we have two input, A1 and A0, right? So two bit register, 2-bit memory and 2-bit input and 1-bit output. That's our state machine. That's something, the first that you need to describe. Then we can write down the Boolean expressions. So unlock equals to S1, no problem, right? Then N1 equals to S0, A1 prime, and A0. Right, just look at this gate. There's 3 input, and there's an inverter here which is connecting A1. A0 is directly connected, and trace back this circuit. This wire is eventually connecting to S0. So it's S0, A1 prime, and A0. Right. Then we can also write down as N0 with S1 prime, S0 prime, A1, A0. Okay, that is this gate, the N1 output. And if it's multiple gates, some AND gate, some OR gate, it shouldn't be very complex if you can draw it. Okay, so once we have this type of Boolean expression, we just go the other way of designing a circuit. We have a circuit, we write down Boolean expression, then if we're designing something, we derive this Boolean expression from the truth table. In this case, we derive the truth table from the expression, from the expression, right? Then for truth table, we try to first lay out all the possible input, and including the current state S1 and 0. So don't think too much, just list all the possibilities, right? For A0 is 0, 1, 0, 1, 0, 1. And for A1 is 0, 0, 1, 1, 0, 0, 1, 1. And for S0 is 4, 0, 4, 1, 4, 0, 4, 1. For S1 is 8, 0, 8, 1s, right? Those are all the possible combinations. Now using this equation, I didn't write S1, it's too straightforward. S1 is directly connected to related to unlock. But we can write down, we can just manually calculate all the possible cases for N1 and 0. For N1 and 0. Then those are the cases, right? Actually, only 2 cases N1 will get 1, and only 1 case N1 will get N0 will get 1. So if we have 4 things, right? If we have 4 elements, only 1 case will get a 1. If I have 3 elements, that means it must come from 2 4-element minterm and combine together. In this case, we have 2 1s in the table. I have 2 1s in the table. You don't really need to calculate this at this time. Just trust me. Okay. Then with this truth table, we know these are the input and output, right? Those are the state and the state, the next state. And the next thing, remember, when we design a finite state machine, we need to do state encoding. So the next task is to do state decode. So previously I draw 0, 0, then replace with state 0. Then 0, 1 we replace with state 1, right? Just replace all the cases. And eventually we'll find the output will only have state 0, 1, 2. There's no state 3. There should be, in theory, state 3. But we have no state 3 at all. That means state 3 is a redundant state. That is not, it's encoded but not used. Right? It's encoded but not used. So in regular cases, we should never go to state 3. In that case, we can basically start to draw the state diagram. So what's the state diagram? Starting from S0, in S0, when can we go to state 1? is this particular input. What's the input? Is basically A, when A equals 3, we go from S3 to S1. Right, we go from S3 to S1. Then from state 1, when we go to state 2, is basically when A equals to 1. So when 3 and 1, it goes to state 2. If it's not 1, we stay in S. Is that a mistake? It should go back to S0, right? Well, let's talk about that later. I think this arrow is a mistake, right? So in S1, if in S1 and we pressed either 0, 1, 0, 2, or 3, we actually should go back to state 0. Let me see which part is wrong. Yeah, we go to state 0, not state 1. So I think it's a mistake. Apologize for this. This arrow should not stay in S1. It should go back to S0. Okay? It should go back to S0, this arrow. Okay? If it's 1, it's go to S2. Then in S2, no matter what we press or what's the input, we go to state 0. We go to state 0, right? So I think there's a question that state 3 can go to state 2, right? But how you can get into state 3? There's no way, right? If you start, if state 0, if we start with state 3, yes, that's possible. But then state 3 is only a transient state, right? Yes. Basically, if we start with state 3, it will go to state 0 or 2 immediately. Then it will stay in this loop of 0, 1, 2. State 0, 1, 2. It will never go back to state 3. So state 3, in this case, we consider it's basically why it goes to state 2 is because not care. We don't care bit. So for the purpose of simplifying this circuit, we remove some input. In this case, this is something we just totally don't care. Okay. So that's why we go to, in that case, we can still go to state 2. But this is something, doesn't matter. So remember, in this case, in this particular point, if we force it to write 0, then this one will be a 4-element term, right? Then it's actually a MOR gate. So in that case, if we draw a kernel map, it's an X there. Then we draw a circle, and it can circle a 1 and an X together. Right? That's why we have this actual state 3, and that can translate to state 2. And it's actually a don't care bit. Okay, then with the state diagram, we basically know what's the purpose of this this circuit, right? It's basically very similar to the secure door or password input circuit. Then in this case, although it's still triggered by button press or by some input sequence, or you can say it's a sequence detector. In that case, our password is 3-1. Okay, if it's 3-1, we go to S2, and whenever we're in S0, we're in an unlock state. Okay, it's just another definition. S0 means unlock. Okay, any questions? So you get the point of how to design a finite state machine and reverse it, right? Reverse it from the circuit. Question?
You mean S2 is unlocked, right?
S1 is well, I'm reusing S2 and S1 here. So this S1 is this bit. I'm saying this bit. Yeah, this is state 2, right? Yeah, don't consider too much about why S1 equals to unlock. This, whatever the circuit is, this is just the circuit design, right? Okay, so we recovered the state diagram and we tried our best to understand what this circuit is doing. Okay, any question? No question? So using the rest of the time, we're going to introduce some commonly seen elements. So the most commonly seen elements in a digital circuit is a counter. For example, in a previous state, we see very common we have 0, 1, 2 state, right? State 0, 1, 2. And this state 1, 2 typically have this type of main path that go through from one state to another, right? In that case, can we have something that just a very common finite state machine, the circuit that's already designed so that we don't really need to design all these state again and again. In that case, we have a counter. So counter is basically a very simple sequential logic circuit that has a n-bit register, right? Then there's a reset bit. Whenever we click reset or feed in the reset signal, we set the value that's stored to 0. Then there's a loop. The output goes back to this adder. Now we have talked about adder. Now this adder is a little bit special. We only add 1 here. Right? Later on, we can see there are use cases if our input is not 1. But basically, what's going on is for every clock cycle, we add the value by 1. For every clock cycle, we add value by 1. Right? Now, eventually, you always need to consider overflow. So if there are 4-bit, then the 4-bit, the largest value is 15. So after 15 cycles, it'll go back to 0. Then after 15 cycles, go back to 0. Okay, so this is an n-bit counter. Now, if you consider this counter as a finite state machine, it's basically the skeleton of this state machine that go back to n minus 1. If you have n bit, right? It's a finite state machine. And starting from this point, you can start to modify it in a certain way that can fit your need by adding more combinational logic for if in what case we go back to what state, or in what case we stay in a state for a little bit longer time. So this is the counter. Then a very common use case is a frequency divider. So we can say if our clock is a very high frequency, right? If our clock signal is 1 megahertz, but if we have a LED light that we only want to it flash in a 0.05 second on and 0.5 second off, right? In that case, our frequency is 1 hertz. So how we can reduce from 1 megahertz down to 1 hertz? Then the very common use is we can design a 20-bit counter. So what's the largest value for 20-bit? 20-bit is 2 to the power of 20, right? 2 to the power of 20, that's 1 mega, right? Remember, 10 is 1 kilo, 20 is 1 mega, 2 to the power of 30 is 1 giga. So 2 to the power of 20 is a 20-bit counter. Then if this is the 20-bit counter, then it actually go a whole circle in every second, not super precise, but roughly 1 second, right? Then we can use the highest bit that for half a second, for half of the million clock cycles, we have a 0. Then for the rest, we have value 1. In that case, if we use that bit to drive the LED, then we can have half second on, half second off. Right. So this is a frequency divider. Then you can reduce the frequency to any frequency you want. Then to extend this frequency divider, then sometimes let's say if our clock signal is 1 megahertz, but we really want something like 22 kilohertz, we cannot go up. We can only go down with a counter. Right? How we can do it? And the quick answer is we can use something called a digitally controlled oscillator. An oscillator is something that goes up and down. Right? In circuit, in a regular circuit, like if you are using a CPU, there's typically a piece of device that is called an oscillator. And in the center of it is a crystal, that some crystal has some intrinsic frequency. Then we amplify the signal, then signal becomes the clock signal, so that the clock signals are generated by some crystal are actually super accurate, right? In that case, that's an oscillator. But what is a digitally controlled oscillator is we use a digital circuit to control the frequency to the desired value, right? In that case, we can produce any frequency that is smaller than the original one. So in that case, how we can do it? It's basically we can use, rather than 1 as the add value, we can use a p value, right? So you can consider if we have 2 to the power of n, if we have p equals 1, we basically have 2 to the power of n. That's how many times we can divide the frequency. We can reduce the frequency. Then if we have a larger p, we can actually tune up the frequency with a higher value of p. So let's do this calculation. Suppose you have a 50 megahertz clock and you want to produce a 500 hertz output. Then typically I can give you n-bit counter, or you can design it any way you want. But in general, the more bit you use, the more hardware resources it will occupy, right? Then fewer bits, that means fewer registers, fewer transistors, smaller die size. But higher bit, that means your granularity is smaller, right? So you're controlling how many, so your granularity is 1 over 2 to the power 24 or 1 over 2 to the power 32, right? You will control the granularity of your control. Now in that case, if you know every clock is 1 over 2 to the power of 32, then you can calculate this p value by comparing your eventual output and your original clock frequency, right? So this p equals to f out divided by f clock and divided by 2 to the power of n. Just put the f clock and 2 to the power n on the other side. Question?
Can you say again what the value of p represents?
The value of p is what you eventually put here. So rather than add 1 in each cycle, you add more. You add p, right? So consider this. If you always add 1, then your output frequency is original frequency divided by 2 to the power of n. Because you count that many times until you can go back. Count that many times, you go back, right? But if you, rather than going 1 by 1, you go 5 by 5. If you go 5 by 5, your frequency is 5 times of going 1 by 1, right? So by doing that, so these two parts will basically say the n will drag the frequency down, but the p will drag the frequency up, right? Eventually, by tuning these two numbers, you can, in theory, produce or approximate any frequency that is smaller than the original frequency. Okay.
So we're basically just counting up by different numbers, and then when it gets to the top, that's a one cycle instead of a frequency.
Yeah. Right. So you count in this register. You add one until you overflow. Then you can consider that overflow, right? That overflow will have the highest bit turn from 1 to 0, right? So if your whole signal, your whole circuit is sensitive to down edge, that is the moment that the rest of your circuit will work at, right? It's the same thing for up edge. It's always the time that you transit from 0 to 1 for your highest bit. Okay, so this is how you can control the frequency. Then we can make it even more fancy. So PWM signal. PWM signal is a type of signal, stands for pulse width modulation. And it's a very, very common signal used in controlling many different things. Like, for example, the brightness of your screen, right? How it's controlled. It's basically controlled in this way. So if you want darker, you just have many screens are actually flickering, right? So on for a short while and off for a short while, because your eye cannot tell. Your eye only tells by brightness. So those many devices are controlled by PWM signal. In typically, if you consider a screen that is controlled by a PWM signal, it's not ideal. It's a relatively cheap, inexpensive solution because the screen is flickering. So some sensitive eyes will feel uncomfortable. But for most of the time, you cannot really feel it. Right? For some LEDs that can tune the brightness, then you can. For some times you're actually tuning the voltage, but for some other time you're actually tuning this PWM signal. Okay. Then also, if you have played something like those cars that follows a track, right? There's a motor that controls the direction, the steering wheel direction. Those are actually also controlled by PWM signal. So, say 50-degree duty cycle, 50% duty cycle that's on and off for the same time. In that case, we'll interpret it as going straight forward. And if you're going down, it will turn to this direction. If you're going up, it will turn to that direction. Okay, so it's very commonly used the signal in digital circuit domain. It can control many different things. In that case, how we can design this type of circuit. How we can design this type of circuit is basically by using this type of clock, but adding a comparator. Now we set a threshold, duty cycle. This is duty cycle is 50% multiplied by 2 to the power of n, right? So if our duty cycle is 50%, then is 2 to the power of n minus 1. Say if we're running at 2 megahertz or we want our frequency to be, if originally we're running at 1 megahertz, and if we want our final PWM signal to be 1 hertz, in that case n should be 20, right? 2 to the power of n should be 1 million. Right, say again. If our original input signal or clock signal is 1 megahertz, and we want our PWM signal runs at 1 hertz, in that case, you need to know, no matter what's our duty cycle, the frequency won't change. The frequency is a fixed value. It's only what part is 1, how long is the 1 and how long is the 0. But the 1 and 0 within one period always add to the period duration, right? So the only thing we're tuning is how long time is the 1, how long time is the 0. In that case, we have a regular counter with n bit that we're tuning down the frequency. But in that case, we also have a threshold that is the duty cycle multiplied by 2 to the power of n. So this counter counts just output a counted value. Okay, it's not the highest bit. It's only the highest value. Sorry, it's the whole n bit, right, as a counter. Now we have a comparator. The comparator is a combinational logic, right? So we'll generate either a 1 or 0. They say if it's greater than something, we generate 1. If it's smaller or equal than, we generate a 0. Right? That is the output of this comparator. Although we haven't introduced this comparator, but from the combinational logic circuit lecture, you should know this is designable, right? We can design it by giving a certain input and certain output. Now we design this threshold. This is the threshold, and this threshold is something that we can change from outside. Given this threshold, we can turn, say, if this is 1 million, we can pass in 0.6 million, then that will give a 60% duty cycle PWM signal. If we make it 0.1 million, then we'll give a 10% duty cycle PWM signal. Okay, then talk about this one. PWM signal, button press detection. It's a very common case for digital circuit design that we want to take some user input, as we said before. Then if we're not pressing it, it's 0 volt. Then if it's connected, fully connected, these two pieces of metal connected, then it's wire connecting this voltage, then the final one is 5 volt. But it will actually fluctuate a lot during this connecting period. We want to get rid of this connecting period. In this case, we actually only want to trigger one signal going through the output of our button press detection logic, right? So how we can design this part, you can check this one. This is a button, right? This is a button. Then this button, we first connect with a register. And this register is a super simple register. You can just consider it as some sort of latch that prevents it from changing super quick. Then after this register, at least it will only change at the edge of a clock cycle, or it will not change at all, right? Now in that case, we push this button here. Then let's consider this gate is connected. So after pushing down this button, then if this value is 1, we actually go to this counter. Then we have an enable signal. That means if this enable signal is 1, we start to count. And if this enable signal is 0, we will stay there, where internal state will not, counting value will not change. That means if this signal goes up, we start to count. If it goes down, we stay at a certain value, right? And also we have this one, if it goes down, we actually reset it. We reset it, and that means, so see this small circle here. The small circle can be either in the enable signal or can be in the reset signal. That means this thing is triggered by low voltage, by 0. That means when our input is 0, that means we reset it, right? In this case, when this signal, button signal decreases from 1 to 0, we reset it to 0. Okay, reset it to 0. So we recount again. So the goal is basically to say, whenever it's up, we need to only consider it's being pressed down after it's being pressed for a short duration, right? Half a second or like 100 millisecond or something, right? So then we only consider, only after clicking, only after pressing it down for a short while, we consider it's pressed. So that's why we need a counter here. And when user release it, or for some reason this voltage is no longer holding, we reset the counter. Then we pass it through to a comparator. Then this comparator is basically a threshold that you can define, say, I press it 50,000 cycles, then we consider it's being really pressed down. Or you can set whatever you want. You can just fine-tune this value according to the latency, if you're sensitive to this latency, or like the physical property of your button used, right? Then we have this signal, the eventual signal that you consider this AND signal, this being going out, right? Then also we need to guarantee this button is being pressed, keep being pressed, so the output signal is going down. So no matter, just if user release it, immediately we'll consider is 0, right? We consider it's released. So that's why AND gate is connected. It must hold, say, above the threshold, or it's really being pressed. Otherwise, it will keep being pressed even if you release it. Then here it goes back to this one. So you have to have this gate so that if it's already pressed, you don't if it's already connected, pressed, you don't enable this counter. Otherwise, you will keep flipping up and down, flipping up and down. If you're pressing it, it's always being pressed, right? So if you don't have this wire going back here and this gate, then you're keep counting, then you're actually generating a PWM signal rather than going up and stay up if you're pressing it. Okay, so this is a counter, and I'm only going to talk about this one component that's commonly used in digital circuit. Okay, then let's talk about memory arrays for the memory part and how the memory is designed. Then remember, when we talk about memory, then we're typically considering registers. But we don't really always to have registers to design memories. There are many different technologies, and different technologies have advantages and disadvantages. But let's look at a generic design that we have an array. This is our memory, right? Then previously, we were considering memory as a register or as a state representation. Now, how many bytes we need to represent the state? We probably need only a few bytes, at most tens of bytes. Tens of bits. Now, in that case, if we want to store data for your computer is several gigabytes of data. Right? In that case, we cannot really use a register to store 1 bit of data. We have to use something more compact and more general interface. So this general interface is designed with an array that you give an address, right? You put in an address. Then if it's a read operation, I input address, I generate the output of data. Then if I want to write data, we put an address and we put data in, then the data is being stored there. So we know it's stored there. Next time we read it, we can get the correct result. That is general design of the memory array. The memory array typically we consider have 2 parameters. The most fundamental parameters. One is the width, one is the depth. Depth means how much data, how many units of data is actually being stored there. Then width means like for each unit, how large is each unit of data. Then if you consider for most of our data today, width is a cache line. A cache line. We'll talk about cache line when we talk about cache, but it's typically 64 bytes or 128 bytes as 1 unit. Then the depth is really depends on how large your data, like 4 gigabytes of data or something, right? Then this is a 1024 word and 32-bit array. That means each unit is a 32-bit data. Then there are 1024 words. I don't really like the words term a lot. Sometimes it can mean different things here, but you can just consider it as 1024 element of 4-byte element. So this is a very good GPU, like part of GPU register. Each register is 4 bytes long, and there are 1,000 registers there are in this GPU. In this, not a GPU, but only a subcore of a GPU. Okay, GPU has many more registers than these things. Then let's look at the organization. The organization is typically in this way. We have something called a word line, and we have the bit line, right? If we want to read or write something, we first pass in the address. Then using the address, we have to first have a decoder. That means we only give an address. This address can be something like 10. Then in that case, we want to light up this line, to enable this line to put it to 1, so that we're saying, or we're enabling this cell, and this cell is connecting to this bit line, right? This bit line. You can consider this bit line as some sort of multiplexer, right? Because we have 4 input and 1 output. Now we're multiplexing the data. But in that case, if you're designing this type of thing, you can turn this, if you're not enable this, you can make this wire, this piece of wire, in high resistant mode. So the data will not flow into it and will not flow out of it. So it's only considered this wire is connecting to this one. Okay, connecting to the data. In that case, store bit 1, store bit 0 and 0. 100 is read out of data 1, data 2, data 1, and data 0. Okay. Then, so this is a bit cell. Then bit cell has a word line and a bit line and a bit that is actually storing the data, right? So when we want to read it, we first select a word line to put a 0 to 1 so that this one is somehow being enabled, and the data actually flows, the voltage flows from here to here. From Z means high resistant mode to a stored value. Now, when we're in the write process, we actually first write the value, we put the value we want to store here in the bit line from high resistance state. Then we enable it. So we enable this one. So kind of we open the gate. We open the gate, then the voltage can flow into, or the charge can flow into the stored bit. Okay. So typically we consider two different types of implementation of this type of array. DRAM, we'll talk about DRAM later. DRAM can be much more complex than this level of introduction. But a very basic thing is what you need to remember with a DRAM is we use one transistor to represent one bit. So this transistor serves as the main part is a capacitor, right? Capacitor hold charges on there are two metal ends, and some sort of medium is in between, so the charge will not escape, right? So it's not connected, so the charge will not flow from one direction to the other. So in that case, the charge is holding on this capacitor. If it has charge, we consider it's 1. If there's no charge, we consider it's 0. DRAM has some big problems that if you read the data, that means there's some charge will eventually say this gate is connected, this transistor is connected, the charge will actually flow to the bit line. That means every time we read some data, we need to write it again. Every time we want to read some data, we need to write it again. That's why DRAM is slow. Also, capacitors has one big problem that the charge will eventually go away, right? It's not battery. The charge will eventually go away, although at a very slow speed. So that means we need to keep refreshing it. So even if we're not using this data, we need to keep writing into this DRAM. That's waste energy. And if we're writing into this part of data we cannot read, that means pretty much a global hiccup. Right, the whole world stops for the DRAM to refresh it. There are many different ways to solve this problem, but it's still refreshing is a challenge for DRAM. So advantage of DRAM is it's very compact. It only needs one transistor. How many transistors is a flip-flop? Like 20 or 20 plus at least, right? It's a flip-flop. But here we can only use one bit to store the data. Then that's your DRAM, that's your memory, 4 GB memory, 16 GB memory in your computer, that's DRAM, okay? And when you turn off your computer, DRAM disappears. So when you start, it's a fresh state. Then another thing is SRAM. So SRAM is controlled by SR latch. This is pretty much an SR latch. Right? In SR latch, remember we have a loop of OR gate, NOR gate, right? So pretty much this is the NOT part of that NOR gate. So you see, this is pretty much an SR latch that keeps data staying here, right? The data is flowing here. It's actually not flowing. It's being locked here. Now, whenever we want to read some data, we just turn this on, so these sides are connected, so we can the data flows to bit line, right? Then how many transistors are there? So remember, we have 2 transistors for each reverter. So in total, we have 6 transistors. I think for SRAM or for register file, 6 transistors to record 1 bit is probably the most important information that you need to remember when designing circuit. That basically dictates how many transistors. It's the most important source of transistors in a chip. So you're remembering the state. Okay. Then typically, when we want to have a brief estimation of the die size, it's very hard to estimate the combination logic. So we just need to remember how many bits of data that we're storing in a register file, right? So consider your register file, like L1 cache, L2 cache, in your computer. There are typically several hundred kilobytes of data in the caches. Your caches are implemented in this type of style. It's much faster. You don't need to write again when you read the data. It consumes more energy and it takes much more space. So it's very hard to have a very large SRAM in your computer because it's a space. Because it takes 6 registers. The register file, I think we can leave this part when we talk about the core architecture. In the core architecture, we're going to come back here. So register file and how we can read multiple register files together and bank the register file. That's something we can talk later. Let's quickly talk about this. We have only 3 minutes time. So read-only memory. Read-only memory, what is read-only memory? Is a memory that you can only read from it. So the manufacturer will directly produce it in that way so that it stores the data. So how this part works is you can basically consider those dots are connected. So if our input is 1, 0, so high voltage will come in from this port, right? Will come in from this port. Here is connected, so data 2 will become 1, but here is not connected. Then this data 1 is 0, data 0 is 0. Right? Second, 1, 0, this line is 1, right? This dot is connected. That means high voltage can flow from here to here, right? But here it is not connected. So data 1 will stay at a low voltage. There's no one is pulling up its voltage. So data 1 will stay at 0. Data 0 will stay at 0. Okay? So if 0, 1 is selected, this one is connected, this one is connected, this one is not connected, that means our output is 1, 1, 0.
For 0, 1, 0, it should be high voltage. It's not connected. Its output is a high voltage.
So data 0 is data. Let's say if no one is selected, our output are 0, right?
Yeah. But
So
the output of the decoder is a high voltage.
It's a high voltage. Yes.
If it connected, it should return it connects to the ground. It should.
Okay. This side is not ground. This side is not ground. You can consider data 2 is connect to the. You can consider this way. Data 2, although I'm drawing this way because it's a mesh. This is data 2, right? It's eventually connecting to here, right? It's connecting to something like this. So data 2 is not drawing down. Can you see it? So data 2 is not connecting to ground, so it's not pulling down. So just don't think too much. If here is 1, then here is high voltage. High voltage. If it's a wire, this side is 1, this side is 1, right? That simple. Then if you have a branch, this side is 1. Then there's another wire, it's not connected. This side is 0, this side is 0. That's it. Okay? Don't think too much about this. But I think we don't have time, so let's continue to talk about read-only memory in the next lecture. Okay.